Hello everyone, how's everybody doing? Today we have an exciting topic, geometry. Yeah, geometry is not the most exciting of subjects. Some people say, Bill, don't you have anything a little more vibrational, vibrating, more energetic than geometry? Well, you got to remember that geometry serves as a bridge between mathematics and physics. So it's a base you really got to cover. And there's nothing wrong with, dotting all the I's and crossing all the T's to make sure you covered every base and that everything is marching smoothly. Um, you know, the keep in mind that the mathematicians, they claim that mathematics is the language of physics. And it's geometry where we have that bridge from mathematics into physics. Historically, that's how it came about. Before I continue with the exciting subject of geometry, let me just remind you we have a conference, Seventh Rational Physics Conference in Borås, Sweden. It's going to be on the 8th of June, and I'd like to remind people constantly so that they know about it and they can make plans and maybe participate. The person who goes there will for sure find a lot of, not a lot, but a group of people that they can discuss physics, real physics with. People who are very well versed in the rope model, and you can exchange ideas, and you will definitely be challenged on your ideas over there. So it's good to get together, in front of a couple of beers and really hash things out. Anyways, one of the things that people tell me, when they discovered the rope model, they say it's a good contribution to physics because it allows them to go in there and at least compare, uh, the rope model that now they heard for the first time against, what the establishment has out there. And yeah, they tell me they like that fact alone, that alone is worth for them, to get familiarized with the rope model. And, but if you ask me, that's not the main contribution to physics that I've made. I consider that maybe a second place contribution. I think the main contribution is having discovered the definition of the word object. And not only that, but in tandem with it, what goes together with that is the realization that not only you can't do physics without objects, but that you need to define this word, and it's very important for the purposes of physics. It all goes together as a package, and I think that's the main contribution. And it also leads us to a related issue, which is that I'm proposing a new version of the scientific method. I'm saying science is something else from what the mathematical physicists are doing, and that has to make you think. Should we go with authority? Should we go with tradition? Or should we analyze this objectively and say, okay, what is physics about? What is science about? And I'm saying that what these people have been doing, I say for the last 400 years, but that's not totally true, because I think that people like Newton and a lot of the people that came in the 18th and 19th century, uh, Faraday, James Maxwell, Fresnel, they were trying to really figure out how this universe works. They were trying to figure out how light works, when they discovered electricity, how magnets work, how gravity works. They really wanted to get to the bottom of these things. And eventually, they came up with the idea of atoms. They wanted to know how atoms behaved as well, what they looked like, that kind of thing. That all stopped in the 20th century, about 100 years ago in the 1920s. Until that time, people still had an interest in knowing how the universe works. By how, I don't mean the description, I mean the why. I mean how in the sense of what is the mechanism that Mother Nature uses. They were interested in that. And for that, you need to identify the objects, the invisible objects. And what came after that is something totally different. They went on the path of math, equations, descriptions, measurement, predictions, observation, gawking, what I call, just observe, and they observe something that is visible, and they have to infer what is invisible, and their inferences were wrong, were irrational, but they continued. And I'm saying none of that is physics. None of that is science. Science is something else. Science is trying to figure out the mechanisms. And you could make a case, and I think a very good case, that up until at least the end of the 19th century, people were interested in finding out, what causes things. They were interested in mechanisms. They were interested in identifying the invisible entities that Mother Nature uses to, like I say, run her shop. And I think that's what really science is about. That's what physics is about. And that's what I call science and physics, and that's what I do. And of course, the mathematicians have no idea what I'm talking about because they say, no, physics is math. Physics is this equation, this description. And I'm saying, no, it's an explanation. It's not a quantitative description. It's a rational explanation. Give me a rational explanation for how light does her magic, how gravity does its magic, how a magnet or how electricity do their magic. That's physics. And so I'm proposing that, even though we intuitively may have had this idea, I'm formalizing it. I'm saying science is about that and not about what the mathematicians do, and what the mathematical physicists do. We have to separate those two. And the question is, how did we arrive with mathematical physics? And the answer to that is that what served as a bridge was this discipline known as geometry. Geometry is, see, if you just do pure math, you're really not doing physics. You have to somehow get in touch with objects, with figures. Not numbers, figures, I mean, geometric figures. And so it's geometry that really serves as the bridge into physics. And so it's worth it to look at and find out if geometry, is standing on solid foundations. I mean, if geometry is standing on quicksand, think about a building. You build it on quicksand. What happens? Well, it falls apart. And so there's nothing wrong with checking to see if geometry really covered all the bases, dotted all the I's, crossed all the T's, and it's on sound footing. So what is geometry? Well, here I have a definition that I brought about last week, and it goes something like this. It says that geometry is a branch of mathematics that deals with shapes and sizes, okay? So that's what it deals with, primarily. In other words, it goes into relations and all that, but primarily, it deals with shapes and sizes. And it continues in saying, and this is, by the way, from one site, but pretty much all sites say the same thing. Geometry, building blocks include undefined terms. Now that's a lousy way to start a discipline. You say it's about shapes and sizes, and then it says, we're going to start by saying that we can't define the, especially the most fundamental terms. And they say some concepts central to geometry are not defined in terms of simpler concepts. The most familiar of these undefined terms are point, line, and plane. Oh my God, it turns out we're going to be doing geometry, we're going to be doing solids, we're going to be doing planes, and all those are made by points, possibly even by lines, and it turns out that we don't have a definition for point, line, or even the plane. That's interesting. And that's more than interesting. It kind of makes should raise a red flag, and it makes you kind of think. Are these people on a sound footing? And they try to define the point, and they just say where an object is leads to the idea of an exact fixed location. So a point apparently is a fixed location. But then they continue to give an example. Say a dot on a sheet of paper. Such things are called representations of points. That's interesting because, a dot and a location are totally, incompatible. One has nothing to do with the other. A dot is a geometric figure and a location is an abstract concept. It's got to do with place. You could say even position. So the question is, of course, if you're trying to blend a concept such as location with a physical object such as a dot, yeah, you're going to have trouble defining that term. And maybe that's where the problem is. With a line, we have the same issue. They define as a row of points extended infinitely in both directions. Infinitely, big problem. Extended, already a problem. Points, it relies on points. I thought we couldn't define a point. So now what are we referring to? Is that point, are we supposed to put the word dot in there or the word location? So, okay, we say these guys, they're not professionals. Where did they get all this stuff? And, when you're looking throughout history, you end up with Mr. Euclid. He's the guy who set up all these definitions or notions or axioms, laws, rules, foundations for geometry already in the days of the Greeks. Let's see what Euclid has to say about it. And this is Mr. Euclid. He says he wrote his book, Elements, and been translated here. What you're looking at is the 1661 version of Elements. And he starts out with three definitions, at least two of them. What a point is, that's that which has no part. And what is a line? A line is breathless length. Okay, not very precise in his definitions. That which has no part has been interpreted as that which has no shape, no size, no dimensions. And then we have a line. What is a line? It's breathless length. What do you mean it's length? You mean a line is a length? Length is an abstract concept. I thought we were talking about geometry, and that geometry dealt with shapes and sizes, primarily shapes. I mean, if you don't have a shape, forget about size, right? So you need a shape, and neither one of these two, neither the point that Euclid defined nor the line definition deal with shapes. And it's interesting that if you go down to definition 13 and 14, you'll find that 14 says a figure is that which is contained by any boundary or boundaries. But then you go to 13 where it goes to the boundary, it says is that which is the extremity of anything. So we got a circular set of definitions. A figure is that which has a perimeter. And what is a perimeter? Is that where a figure ends. It's the fence where a figure ends. So we don't have a definition of what a figure is, or essentially what a shape is, what an object is. And of course, he didn't apply those two to the point or the line because he's using concepts to define point and line. So Euclid did not have a good grasp of definitions, of scientific definitions, and that was our starting point. Okay, so we started off on the wrong foot. That was 2,000 years ago. Obviously, we must have made significant progress since then, right? Okay, let's find out. Well, let's go see Dr. Math. He must know what points and lines in geometry are all about. So Dr. Math, he writes a book known as Introduction, or introduces geometry. It's an introduction to geometry, right? Okay, so what are these points, lines? What is geometry about in general? So he says points, lines, and planes correspond to talking about no dimensions, one dimension, and two dimensions in the coordinate plane. Okay, so he relates these three words, point, lines, and planes, to dimensions. A line is one dimensional, since one number, the distance from zero tells you where you are. Okay, so that's a line, where you are. A plane is two-dimensional since you need x and y to locate a point. Okay, what's that got to do with what a plane is? And then a point is dimensionless. Again, none of those three definitions have anything to do with physics or even with geometry. They're talking about concepts. If geometry is about shapes, as a minimum, you would think that you could define what a point is, what a line is, what a plane is. And these guys are saying that they're just giving you a mathematical description. They say a line requires one number. So what? And a plane requires two numbers to locate a point within it. And what is a point? Well, it's dimension. You don't need any lines to, or any points, or any numbers to designate a point. And it gives you, he says, following that, it says, it consists of only location. That's what a point does, right? It consists of only location. So it's only possible to be one place if you're on a point. You don't need any extra numbers to tell you where you are. Points, lines, and planes are foundations of the whole system of geometry. Oh, good. Big words there. But then he says, but point, line, and plane are all undefined terms. How can that be? And here's the explanation. Well, any definition we could give them would depend on the definition of some other mathematical idea that these three terms help define. In other words, the definition would be circular. That's essentially the worldly wisdom today across the board. That's what all these people believe in. Or how they explain it. They say, we can't define these terms because we would need more words, and those would have to be defined. And since these are the foundations of everything else, that's like the buck stops there. That's the bottom line. Okay, so not much progress from Mr. Math from the days of Euclid. We're still suffering for definitions. Okay, let's see if we go to a more respectable site, more authoritative site. Okay, let's go to Wolfram. They pride themselves in saying, here you see it in their title, it says, the web's most extensive mathematics resource. Oh my God. And it says, built on mathematical technology. Okay, whatever that is. Okay, so here we have a respectable source. What do they say about geometry? Well, they say, again, it's the study of figures in a space of a given number of dimensions and of a given type. And that definition is more or less corroborated by the Wikipedia. It says geometry is a branch of mathematics concerned with questions of shape, size, relative positions of figures, and the properties of space. As you can see, they use these words figures and space. So we just need to find out what they refer to when they're using these words. What is space? What is a figure? And so when we look at, Wolfram, we look up the word space, and yeah, they do have something here. Where is it here? And they say space. The concept of a space is an extremely general and important mathematical construct. Okay, good. That's a good start. Let's see what it is. And they just go and continue. Members of the space obey certain addition properties. Spaces which have been investigated and found to be of interest are usually named after one or more of their investigators. This practice unfortunately leads to names which give very little insight into the relevant properties of a given space. And they go on and talk about couple words about Euclidean, Minkowski, and topological spaces. Never once does Wolfram define what a space is. And they give all these examples of all the spaces, all these name spaces that they just mentioned, but they never define what a space is. So we don't know what a space is. Let's see if the Wikipedia can do any better. And the Wikipedia says, okay, it says space, okay? In mathematics, a space is a set, sometimes called a universe, with some added structure. Okay, so we have a set and structure. What is a set? Well, they continue to say, a space consists of selected mathematical objects. My God, what could a mathematical object be? I know what an object is, but I don't know what a mathematical object is. So let's find out what all these words mean. Space is a set. Let's see. In mathematics, a set is a collection of distinct objects, okay, considered as an object in its own right. For example, the numbers 2, 4, and 6 are distinct objects. These are objects? A 2 is an object? Wow, I don't know about that. I know a table is an object. I know a dog is an object. I know a tree is an object, but I never knew number 2 is an object. I thought number 2 was a concept. And in fact, they say the concept of a set is one of the most fundamental in mathematics. Okay, so it's one of the most fundamental, and they say that it's a collection of objects, and the objects are numbers. So what have we learned? Okay, so let's see if we can find out what a mathematical object is. Again, it's an abstract object. That's what a mathematical object is. Okay, what is an abstract object? Well, it has no physical reference, whereas a concrete objects do. We still don't know what an object is. All we know that it's got no physical, it's nothing physical. Okay, and it says they are most commonly used in philosophy and semantics. So we got a problem here because these people say that mathematics is the language of physics. And what do they talk about? They talk about abstractions, and they say that these have to do primarily with philosophy and semantics. Then they accuse me of doing semantics. It turns out that these people are doing semantics and they call it doing physics because they say that mathematics is the language of physics. So we got a problem. And again, we're talking about how they're applying all this to geometry, which is the physical bridge to physics. Okay, so keep that in mind. Okay, that's in the background here. Okay, what is a structure? They had the word structure. They added structure. A general definition of structure proposed by Bourbaki embraces all common types of spaces, provides a general definition of isomorphism, and justifies the transfer of properties between isomorphic structures. So what is the definition of structure? Well, it's the transfer of properties between structures. Great. So what have we learned? We haven't learned much. But I like the last line because that one puts everything in perspective. While modern mathematics uses many types of spaces, such as la 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 la, it does not define the notion of space itself. So now we know what a space is. Space is that which has never been defined. So we have Wolfram, and Wolfram says, talks about spaces. That's what they do, I guess, for a living. And they don't define it. They just name different. They have all these different kinds of spaces, Minkowski space and Euclidean space and all these named spaces. But they don't know what a space is because they can't define it. They haven't defined it. Okay, have they defined the word figure? Another important word because if physics deals with shapes and figures, right? Some kind of thing, some object, right? What is a figure? Well, you saw that Euclid couldn't define it. He said, a figure is what ends in a perimeter. And what is a perimeter? It's what holds whatever is ending there. So he's got a circular definition. But hopefully, after 2,000 years, Wolfram can do a little better. And here it is. They say they don't have a definition for figure, but they say, oh, but we have found impossible figures. It's in a class of illusion in which an object which is physically unrealizable is apparently depicted. Okay, we still don't know what a figure is, but they're already talking about it. And they go through what an illusion is. An illusion is an object or drawing which appears to have properties which are physically impossible, deceptive, or counterintuitive. So they never define the word figure, they just start using it. They do have the word object, but when you look it up, it says a mathematical structure. And again, we don't know what a structure is because they've never defined that word very well. And it's a mathematical structure in a category. Great. What have we learned? Here we have the word structure in Wikipedia. It says a structure on a set is an additional mathematical object that in some manner attaches to that set to endow it with some additional meaning or significance. Well, so far all we have is no significance, no meaning. We don't understand squat. We haven't learned anything. These people have circular arguments. No wonder they can't define any word because they never learned how to define words scientifically. And people sometimes accuse me and they say, well, Bill, you play a lot of semantic games and, we want to do physics. We don't want to do grammar. See, the first thing you should realize is all these people from Euclid onwards, they try to formalize, they try to define the foundations of geometry. That's why they took the trouble to write all this stuff, because if definitions are not important, they could have continued and say, well, we're not going to define any term. We're just going to run with our intuition. They didn't do that. They sat down and they tried to define words. They were just not successful. That's the problem. They were not successful, but they claim later on, sweeping statements saying that mathematics is the language of physics. And they can't even define their own language of mathematics. They're telling you that in so many words in your face. They're saying, we don't know what a point is, we don't know what a line is, we don't know what a space is, we don't know what a figure is, but let's continue. So why did they take the trouble in the first place? Then the other issue is that you do need to establish the foundations of a discipline, because you need to establish what is the, what are the limits of the discipline. You have to find out, are we going to include medicine within physics or within geometry? Medicine, I think, is outside the bounds of geometry, right? I would think. And so, you have to define the limits of the different disciplines. For this, you need words. So you need to define certain terms. You need to establish the foundations. And again, I got a problem with these people because, I have different foundations. I'm saying that, again, my number one contribution to science was not really the rope. That's my second contribution. My first one was the definition of the word object. You need to know what an object is for the purposes of physics. And what this does is also establish that physics is something else than what we've been doing in the last 100 years. Physics has to do with objects, not with math. And these people say that they have a different, my golden principle says you can't do physics without an object. Physics requires an object. And they're saying something else. They're saying you can't do physics without math. You need math, and maybe you need predictions, and maybe you need experiments, and you need verification and observation, and equations and measurement. And I'm saying we don't need any of that. We need rational explanations. So there is a difference in foundations. I'm saying we need physics has to do with rational explanations of mechanisms. These people are saying, no, physics is descriptions, mathematical descriptions. And so what you should ask yourself is, if physics is just mathematical descriptions, aren't we interested, or within physics, don't we study, aren't we interested in finding out how a magnet attracts another? Aren't we interested in figuring out, why a spoon falls to the floor, not to the ceiling? Are those issues of physics? Are those questions of physics? Subject matter of physics? If they are, the mathematicians will never pinpoint them, will never figure them out, because they're doing something else. They're doing, oh no, we measure. And then we create an equation to describe the measurement, what happened, and that's physics. And what's the physical interpretation? Oh, we think it's done by angels, or, particles are doing this, or they can tell you whatever, because they say, well, that's not physics anyway. That's ontology. That's philosophy. That's metaphysics. Physics is the mathematical description. We're done. We already measured. We gave you the equation. What else do you want? And so we got a problem because I'm saying that, up to the 19th century, people were interested in finding out the mechanisms, what the invisible entities were. And that stopped from 1920s onwards. Okay. And so we have a difference in there in foundation. I'm saying that that's my contribution. I'm saying I've reinvented physics, you could say, or brought back, you could say, classical physics, and say, look, what these guys were trying to do, that was physics. They were trying to figure out how this universe works. I thought that was what physics was all about, trying to figure out, how it works. And by how, I mean why, what causes it to work. And you can't figure that out with math. Math just tells you how, but another kind of how. Tells you just a description saying, yeah, the earth goes around the sun. And it goes so fast in so many minutes and so many years, they just describe. And if you want an explanation for how, or, what is causing that to happen, what causes gravity, what causes light, what causes magnetism, they say, oh, you're doing ontology, you're doing metaphysics. That's not part of physics. And that's where we have a problem. Because if we have no explanations for some of these phenomena today, is because we're doing math and not physics. And it's geometry that took us there. So we do need to find out what geometry is about. You can see that these people haven't defined the terms, the foundations of geometry. So they built this castle on quicksand. And you say, well, how can that be? We've been doing geometry for 2,000 years. And you're saying that it's not on a solid foundation. All the axioms, all these angles and, volumes and areas and so on that they've calculated, all that's worthless. Well, I'm saying that, you need to establish the foundations. And I'm saying the foundations are not there. They haven't defined the word space. They haven't defined what a figure is. They haven't defined what a point is, which is their bread and butter. It's their building block. They haven't defined what a line is. They don't know what a plane is. They say they can't define any of these terms. And, at some point you got to figure out, whether what they're doing is science, has anything to do with science. I thought science had to start with rigid, rigorous definitions, solid definitions, because that's what the foundations of science are. If you're just not going to go past it and say, well, I'm not concerned about that, we'll let someone else do that. See, they're pushing all these things, the responsibility for all that, to English majors, to librarians. They're saying, well, or philosophers, they say, we do physics here. Well, what is the definition of a point? Oh, you got to go to the other side of campus for that. See, the definition of point is determined by all these librarians, English majors, and philosophers. They deal with those definitions. We just use whatever they give us. So we got a problem because these people are talking to each other. They're in different disciplines. It's like they're saying, the definition of the word point is not part of our discipline. It's not part of geometry. We don't deal with that. That's librarians that deal with that. We just deal with using the point. And what is a point? Well, go ask the librarian. We just borrow whatever they defined. That's the problem. The problem is that these people are using terms which they haven't defined. They don't know what they are, but they say, we're going to use them anyways. You know what we mean, wink, wink, nudge, nudge. You know what we mean. So they want you to intuitively understand what they're talking about. And it's very simple, they just can't define these things. Here we have Wolfram trying to define the word point. And here, again, we're talking about an authoritative source, right? These people are authorities. And they say, look, a point is a zero-dimensional mathematical object, whatever that means. Because if it's zero-dimensional, it's not an object. If it's a mathematical object, whatever that is, a 2 or a 3 or a 4, again, it's meaningless what they're talking about. Now, obviously, they're talking about abstractions. It says, which can be specified in n-dimensional space using an n-tuple. In other words, what they're using is ordered pairs or triplets or whatever, right? And so you can see the pictures on the bottom. I put the blue images there, or words, whatever, letters. Um, they're saying, here you have the point P on a plane, and you have another point P on a cube, okay, on a solid. And what is that point P? Well, they're saying it's an ordered pair or an ordered triplet. They're saying it's an entuple. And each one of those, by the way, is in their language is a dimension. So they can have infinite dimensions. They can have all the letters in the alphabet and then some. Okay, so they're talking about the location of the point P. They designate that with a little dot. And so the question is, is the dot the point, or is the location a point? Are we talking about the elephant that is at that location, or are we talking about the location when we get rid of the elephant? And you say, well, obviously, the point, it refers to the location. Well, why don't they call it location? Okay? Why don't they call it location and not point? Why do they have to call it point and designate it with a dot if they're talking about locations? And here you can see, although the notion of a point is intuitively rather clear, the mathematical machinery used to deal with points and point-like objects can be surprisingly slippery. No kidding, because they never defined, these words. They never defined what a point is. And then here you have the definition of the word line from, again, from Wolfram. And they say, look, a line is a straight one-dimensional figure. And they show one at the bottom, which to me looks more like a two-dimensional figure. The fact that I can see it points to the fact that that we're looking at a two-dimensional elongated rectangle. That's what a line is. I mean, objectively. And it says extending infinitely in both directions. Well, if it extends infinitely, obviously it's not bounded. And hopefully in physics, all objects are bounded. So what does this line have to do with physics if it's still growing, if it's still extending and we can't see the end of it? So again, they've got they say that mathematics is the language of physics, that geometry in a way, is the bridge, the language of physics. And here they're talking about stuff that has nothing to do with physics. First of all, what I'm staring at is not one-dimensional, and neither is the point a zero-dimensional entity. Second, they haven't defined the word figure, but I'll take this as a figure. And the figure that I'm seeing is a two-dimensional rectangle, and they're saying, no, it's one-dimensional when my eyes tell me something different. So they're trying to believe, they're selling me a used car here, and they say it's infinite, which again has nothing to do with physics, because it means that this thing is not bounded, which is what Euclid at least defined a figure as. He says a figure is something that ends at a boundary, and this guy has no boundary. I put, by the way, the plus infinite and negative infinite there just to illustrate the fact that this thing continues on forever. So when they finish building their line, I'll find out what it is. But it turns out that, they're referring to, not a figure like they say they're a straight one-dimensional figure. That's not what it is. It's what Euclid defined. It's length of distance. And they're talking about distance traveled. They're saying, this is an itinerary. It's not even a line. It's not a geometric figure. And so we got a problem here, because the question is, if mathematics, specifically geometry, is the language of physics, but these guys are talking about abstractions, they're not talking about figures, they're not talking about objects, then how can they claim that geometry, mathematics in general, is the language of physics? We have a problem here. This is a serious problem, because these people are entering a field for which they have not even set the foundations, and a field that by their own reckoning, by their own foundations, the ones that they want to establish, not only have they not defined the terms, but it has nothing to do with physics. It has to do with abstractions. They put a line there, and you say, okay, a line belongs to physics because it's a rectangle. So you can say, well, okay, it deals with this object, this figure, this shape that I see in front of me. But the shape that you're seeing is not what they call a line. A line is an abstract concept that is not really one-dimensional. It's non-dimensional. What they're saying with the one-dimensional phrase there, that label, is that you need only one number to designate a point on the line. That's what they're saying. They're talking about a distance again from some arbitrary point to where you ended. That's where the line ends. But it turns out that's not a line, that's a line segment. The line continues infinitely and is not even a geometric figure. So all this stuff, you can see why they couldn't define it, because all this stuff is just a big mess. It's a big mess because they've never defined the bread and butter of geometry. Okay, there's major problems with geometry, with the foundations of geometry. And if there's major problems within mathematics, much less can that be considered as a foundation for physics. Mathematics has nothing to do with physics, first, because mathematics is just a description. But second, or more fundamental yet, is that the foundations of geometry, which is supposed to be the bridge, have never been established, at least from a physical point of view. It's all abstractions. The point is not a point. In other words, a point is not a dot, it's a location. A line is not a stick, it's an itinerary. And so they take this itinerary and say, oh, with this itinerary, we're going to build planes and solids. No way. You don't build planes and solids, you know, with itineraries. You can build them with sticks. You need bricks to build something. And this is not a brick. This is an itinerary. This is a verb. You can't use a verb to construct solids. So the foundations are not there. Something is terribly wrong with the foundations of geometry, and it's always been like that. It's never changed. These people have simply jumped over, skipped over the foundations of geometry and just kept going, and then extrapolated that onto physics and said, oh, by the way, you know, we are the foundations of physics also. No way, the foundations of physics are objects, and there are no objects in geometry. There are ideal objects which, again, don't exist in nature, don't exist in real physics, and that's only includes the solids. That's the only branch that fits in with physics. And then the planes, the lines, and the points, the things that they can't define, they have nothing to do with physics, and they have nothing to do with reality. Those are things that are used for calculations. They say, I can calculate an angle. Okay, so you can calculate an angle. I can calculate an area. Okay, you can calculate an area. I can calculate a volume. So what? What's that got to do with physics? Physics has to do with, you know, tell me how gravity works. You know, what causes gravity? That's what physics is about. And if you're just going to say, well, mathematics is physics and just the description is mathematical, quantitative description is equivalent to physics, well, yeah, you'll never answer those questions. See, people ask qualitative type of questions. You know, how does the atom work? And they say, well, let me show you the distribution, the probability function. And I just want to know how the atom is constructed and how the electron goes around and that kind of thing, you know. And these people are talking about, you know, probability functions. What's that got to do with how the atom works? And this is we'll never find out, we'll never figure this out as long as we continue thinking that mathematics is the language of physics. Okay, so let's get down to what really physics is about. And here I put, you know, the first golden principle, as I call it. This principle is sine qua non. You absolutely need it. And I'm saying this is my main contribution to physics, not so much the rope. Rope, I'll put that as number 2. The first one is here. Physics requires an object. No one in 10,000 years figured that out. You know, it's like nobody saw it. They say, oh, we need math. Well, don't we need objects to do physics? I mean, do we need math? If there are no objects in the universe, can you do something with your math? What is your math worth if there are no objects? If we remove all the galaxies, all the stars, all the atoms, all the planets, everything, every gas, everything that's out there, what's going on? What's happening? What are you observing? What experiment can you do? See, you need objects to do physics, and they never realized that. And obviously, if you need an object to do physics, and that's your first principle for physics, the next item on your action item list is that you need to define what an object is. And we define an object as that which has shape. And that's what Euclid was referring to when he tried to define, in his clumsy way, what a figure is. He said, it's that which has a perimeter, and perimeter is that which stops an object from growing. That's essentially what he said. So it was a circular definition. Here we're saying it's that which has shape. And people say, well, Bill, can you tell me what a shape is? And the answer is, I don't need to. Because we need to define it for physics, and we just have to select from different criteria. We have, volume, we have mass, we have that which moves, that which is made of something, and we have all these things with which we can compare the word shape is. Do we need to know exactly what mass is? Do we need to know exactly what volume is? No, we just need to know which criteria to use. Should we, or which criterion to use? In this case, we're going to compare shape against motion, against volume, against mass, and we got to choose one. And the one we're going to choose is shape. We're not going to choose mass, because mass, all the others essentially are built on motion, and motion requires two locations of an object. That means it's like requiring two objects. What is a concept? We need to distinguish objects from concepts, and it's a word that invokes or embodies two objects, which means that you're going to need to define the word object before you define the word concept. That's the first issue. The second issue is that every word in the dictionary can be placed under one of these two categories. It's either an object or a concept. Okay, and then for all practical purposes, a concept is that which doesn't have shape. And the main concept involved in physics, you could say it's not involved in physics really, because we don't need it. It's just serves as a background, and that's the word space. If something is that which has shape, nothing is the antonym and means that which doesn't have shape. And the synonyms include space, vacuum, void, etc. Okay. So once we define that, and we say, okay, we know now what an object is. And the next question people have is, well, is really a concept a word that invokes or embodies two objects? Is that really true? I mean, I'd hate to test it on every word in the dictionary. There are thousands of words in there. I mean, how can we be sure of that? Well, here's one way that you can check that out, on your own. Here you have parts of speech, okay? And you have different things in there. You have different types of words. And, you have these different categories of words, and you have articles, you have prepositions, adjectives, adverbs, verbs, conjunctions, pronouns, nouns. Those are the primary ones. And if you read through each one of these, you'll find out that in all cases, you are essentially invoking or embodying two words, two things, or two concepts in some cases. But again, what is a concept? It has to do with the word two, with a concept of two, and it's either an object, two objects, or two words treated as objects. And an article is used to modify a noun. So what's the purpose of the article? Is to modify a noun. You need the noun, so it alludes directly or indirectly to a noun. What is a preposition? Again, it indicates location, near, beside, or on top of some other noun, or between two nouns, or pronouns, or some two things. What is an adjective? It's a word that describes a noun. What is an adverb? A word that modifies or qualifies an adjective, verb, adverb, or word group, etc., etc. So it always refers to something else as well. Verb, action, state, or occurrence, and forming the main part of a predicate of sentence. What is an action? It involves two locations of an object. So it's like you're treating the second location as a second object. You need two frames in a universal film to have a verb, an action. Conjunction, a word used to connect clauses. So again, we're talking about two. Pronoun, same thing. A word that can function as a noun phrase used by itself, and that refers to either to the participants in the discourse, like I, you. I means that there is you, and you means that there is I, or he, or she, or something, or to someone or something mentioned elsewhere in the discourse. So in all cases, all these parts of speech, they invoke or embody or in some way introduce or allude to a second object or two objects, or words treated as objects. And the noun is a weird one, and that's why we have to be careful with the word noun. Um, a noun, for the purposes of physics, okay, we got to keep this in mind. For the purposes of physics, only objects can serve as nouns. We can't use the word motion. Motion in ordinary speech is a noun. But that word motion cannot be introduced into physics as a noun, as a subject of a sentence, as an object that performs an action. Okay? And you say, well, why do you say noun? You're redefining the word noun. Do you need to do that? Can't you just say, well, physics is done with objects? Well, there's a problem with that. The problem is that the statements that you make in physics, if we're going to do it formally, if we're going to do it right, then the subject of the sentence cannot be a verb. You cannot talk about motion. You cannot talk about orbit. You cannot talk about itinerary. Those are verbs. The correct way is to say Jupiter orbits. Jupiter is the noun, orbits is what it does. That's the correct way. Now, nothing wrong with saying the orbit of Jupiter. Okay? Nothing wrong with that. Except that we need to identify which one is the noun, which one is the subject. The subject is the thing, and the thing is Jupiter. And the problem is we get so used to using ordinary speech in a scientific context that we forget about that. And we start talking about fields as if they were object. We talk about energy as if it were an object, or mass or time. All these become objects. Now we bend time. Now we move a mass, we transfer energy. That's where the problem comes in. Because now we've converted ordinary speech, we introduced that into physics, and now we forget about the fact that these are not nouns, these are not subjects of a sentence. They can't be in physics, but we treat them as such. And that's where we get confused. We lose track of what these words mean, what they really mean. All these are concepts, and concepts cannot serve as the noun in a sentence of physics. That's why I use the word noun to refer to objects only. There is a reason. It's not that I just want to change the language for the hell of it and say, well, you're making it more complicated than it is. No. It's that a statement of physics can only have as an object, as a subject of the sentence, only can have an object as the noun in a sentence. The predicate has to be, all these verbs. And that's where the problem is. They begin to talk about waves as physical objects. Time is a physical object. That's where the danger is. That's where the problem is. They forget about where all this came from. Anyways, let's get down to the conclusions here. Saying that geometry has no solid foundations, therefore, it's cannot be used in physics, essentially. Geometers have no definition for the key words, space and figure. Okay, these two words have never been defined. And for sure, physics deals with figures, with objects, as I call them, first and foremost. And the word space is really weird, because space is nothing. It's a synonym of nothing. It's a synonym of vacuum, of emptiness. And they talk about three-dimensional space, two-dimensional space, and four-dimensional space, and all these dimensions that space has. Space has no dimensions. And again, it's this ordinary speech that has penetrated physics. Space is treated like a physical object. They talk about the dimensions of space. No, it's the objects that have dimensions, not space. Space has no dimensions whatsoever. It's non-dimensional. It's a concept. All concepts have no dimensions whatsoever. You can't talk about the dimensions of love, not in physics. Nevertheless, none of the fundamental figures with which geometers build their discipline are defined or even qualify as figures. A point is not a figure, it's a location. And a line is an itinerary, not a stick. So these are not figures. And therefore, if geometry is a study of figures, of shapes, these do not qualify as figures, as geometric figures. The point is depicted as a dot, but means location. Geometers claim that it is 0D when the object we're staring at is patently 2D. You're looking at a dot, which is as a minimum 2D, maybe it's 3D. Imagine you had to talk to Klingon. Klingon visits us, he's got a different language. And you say, look, this is a point. And you put a dot on the board or on a piece of paper. And he says, okay, he looks at it, what does he see? He sees a two-dimensional object. You say, okay, I know what a point is. That's what he thinks. He says it's that little smudge that you made on the paper. It's two-dimensional. And then you tell him, oh, by the way, it's zero-dimensional. He's going to have a contradiction in his mind. You say, what do you mean? I'm looking at something that's two-dimensional. And the line is illustrated as an elongated 2D box. Geometers tell you that you are staring at a 1D line. No way. If it's a 1D line, they're talking about something else. They're talking about location along an itinerary, or they're talking about the itinerary itself, or length or distance traveled or whatever, then that's not a geometric figure. Don't tell me that that 2D box is one-dimensional. And geometers never realize that you don't define objects, you point to them. That's a major failure of geometers. See, they said, we can't define the point, we can't define the line. Of course you can't, because you don't define objects, not in rational physics. What you do is you point to them and name them. If you want the Klingon to understand what a table is, you point and you say table. Now he knows what a table is. You don't define it. You don't say, look, a chair is something that's got 4 legs, a seat, and a backrest. He still doesn't know what you're talking about. But if you point and say, look, that's a chair. Oh, okay, I know what you meant by chair now. It's that thing that you pointed to over there. See, and geometers never discovered that you don't define geometric figures. What you do is, and that's what they do, they strain their minds and they say, how do I define a point? How do I define a line? How do I define a plane? Well, I can't define it, so I'll just leave it like that and I'll say that it's undefined. No. The way it's very simple. You make a dot on the board and you say, that's a dot. You want to call it a point? Fine. Call it a point. But don't tell me that a point is zero-dimensional or that it's a location, because that's not what I drew on the board. What is staring at me is a dot, and that is a figure. If you're going to say that the word point means location, just use the word location. Don't use the word point to confuse me. Okay? And don't draw a dot to confuse me. And then the last one is geometry is not and cannot serve as a bridge between mathematics and physics because it works with abstractions. Physics deals with objects. Abstractions and physical are antonyms. So if these people are working with abstractions, first of all, they're not working with physics. Second, they can't claim that mathematics is the language of physics. And certainly geometry cannot serve as the bridge between mathematics and physics. With that, I'll see you next time around. I'll continue with line. And I'm sorry if it's a boring subject, but we need to cover this space, And again, one of the reasons I cover these things is to make sure that you understand that where a lot of the misconceptions that we have today in physics, so-called physics, mathematical physics, come from. They come from the fact that these people have taken mathematics and extrapolated it onto physics. They said, that's physics. No, that ain't physics. Physics is explain to me how gravity works. Explain to me how a magnet attracts another. That's physics. And if that's not physics, what is it? Please tell me. Is attraction between the magnets, how it does it, is that not subject matter of physics? And if the answer, if you give to that question is yes, it is, then these people will never figure it out with math, because all they can do is describe with an equation what is happening, and then they give you a bogus, explanation. Say, well, I think it's done, with particles or waves or fields or whatever. They give you any word in there and they say, oh, we can't define it, but that's how we interpret it. But anyways, that's not part of physics. That's ontology. That's philosophy of physics. Physics is just the objective description, mathematical description, right? And so we'll never have an answer. And we don't have any answers to those questions today because of that, because we allowed the mathematicians to take over. It's like, the religious people have taken over atheism, something like that. Okay, so we'll see you next time and we'll continue with line. So if you're not interested in geometry, now you know what the subject matter will be next time around. I'll continue with line and hopefully I can cover a couple other subjects as well. I'm going to be covering planes and dimension. We'll see how much I can cover. We'll see you next time. Bye-bye.